and this is the Nautilus, the ROV that we have built for the 2019 meets ROV competition. Safety is an extremely important aspect of the team. That is why we have safety 25 amp inline fuse on our power supply. We also have IP20 motor guards, as well as warning sticker on all moving parts, including the fully shrouded propellers. We have string relief on wires on the ROV, and that exits the control box. And we also have string relief on the power connector as well. Now, in addition to the main recommended safety features, we have also implemented some of our own safety features. These include a current and temperature limit on the ESC's controllers. We also have, which prevents voltage spikes and failures. We also have leak, humidity, and inner temperature sensors. For safety procedures, we have a pressure pump that we pump the housing to 350 millimeters of mercury to simulate pool depth. We also developed a similar method for our servo motors to test them at that depth. And we follow a safety checklist which has normal operation of the robot and also in case of emergencies.
In order to repair damage, observe underwater habitats, and locate historical artifacts, we need a reliable frame system. Our frame system consists of HDPP, which is an acronym for high-density polypropylene. We use this material because it is stronger and more flexible than other materials that we could have used. Because we custom-made our frame system and we CNC machined it with a local company, we were able to integrate vector motor mounts, claw designs, and also custom handles. These custom handles also aid in buoyancy. They're made out of close-up cross-linked polyethylene. We chose our material by using a decision matrix that included buoyancy and density, as well as compression and water absorption even at high depths. We also have this electronic housing, which is 76 millimeters in diameter and is acrylic and clear in order to help with troubleshooting.
For our housing, we have two entrances for cables, the front and the back. On both sides, there are cable penetrators that are waterproof with marine-grade epoxy. With the epoxy, the whole housing can withstand up to 70 psi of water pressure. With this, we've chosen to use 6 and 100 brushless motors, 2 for up and down movement and 4 for vector movement. Just like the cable penetrators, we waterproof the wires of the motors with the clear epoxy so we can see any corrosion or cracking that has occurred. We used a design matrix to choose these because they were 1, they could withstand harsh marine environments, 2, their small size reduces the overall drag, and 3, they're a lot more efficient than traditional underwater brush motors.
This year's robot also incorporates our company's custom thrusters, you can see here. Our motor shrouds and guards were printed using PLA, while propellers were printed using ABS, which is stronger. By customly making our thrusters, not only was it cost effective, but also allowed us to integrate it into our custom frame, because obviously this would have not been able to have been done with pre-made parts.
To control our ROV with a reliable and space-efficient electrical system, we had a numerous amount of custom printed circuit boards. So, starting with the control box, we have the circuit boards are designed using the ECDA, a free-online software, and they're all based on the Atmel AVR microchip microcontrollers. So starting with the control box, we have the board called Topside Communication, also known as TSC. The TSC utilizes the ATmega 2560 and has multiple serial outputs for communication for both in and out.
We use Full Duplex RS-45 communication systems for the main and micro ROV. We use Full Duplex for the main ROV because it has sensors and requires sensor data, while the micro ROV does not. Our tether, which you can see here, has 2 10-gauge power wires and 4 twisted 26-gauge cable wires for the RS-45 communication system, as well as ultra-thin coaxial cables for the cameras. Our cameras are hooked up to fully isolated power supplies in order to eliminate flickering, which was a main problem last year.
The power supply also protects against 50 volts of power surge for up to 100 milliseconds. Now, our main electronic housing consists of 3 main PCBs. The first board is called the servo controller and RS-45 converter. That takes the RS-45 signal from the tether and converts it into TTL, transistor logic, for all the circuit boards. And then this board also takes that TTL signal and converts it into pulse width modulations in order to move the servos accurately.
Our second custom printed circuit board is our sensor board. This incorporates 4 leak sensors, which are 2 are located at each end of the housing, a DHT11 sensor which monitors humidity and temperature inside the housing, as well as a temperature probe located under the ROV to read temperature of the water.
Now, our third and final board is the vector controller board, and this also utilizes the MEGA2560 and converts the signal sent from the tether into pulse width modulation signals for the ESCs. The ESCs are mounted on an aluminum plate. The reason why it's aluminum is because it helps with heat dissipation and thus increasing the efficiencies of the ESCs. The ESCs run our custom programmed via Heli32 software, and which allowed us to implement safety features such as current limits and temperature protection that would otherwise be unavailable. All the PCBs inside the enclosure use connectors so that they're all modular in case of failure, and even the ESC board here uses Anderson power pole connectors for all the brushless motors, so this can easily be detached in case we need replacements.
Arduino IDE was used to program all the boards. Data was sent as a character array at a baud rate of 57,600 bits per second and was interpreted as a string. This allowed for speed control and also vector control. So for speed control, we used the current limit. So when 2 motors were running, they each received more current as opposed to when 4 motors were running.
We built our custom GUI using Python, which allowed us to have vision processing, video display, and serial communication, all running simultaneously using multi-threading. So on the enter key on the control box's keyboard switches between 3 toggle modes: no vision, benthic species, and live measurement for the measurement of cracks in task 1. For the vision processing, we use a method called you only look once, YOLO detection, which builds upon convolutional neural networks. But before that, the image is first blurred, thresholded, and masked so that it's pre-processed and ready to be processed by the network.
So using the thresholded images, we used Darknet to train the YOLO model, and with 53 layers. So after we created the model, so that proved to have it was an easy identification of shapes. Also gave us low variance and low error of the accuracies between training and test and databases. We use YOLO because it uses non-max suppression, which generates optimal non-overlapping bounding boxes around image contours.
For our manipulators, we have custom 3D printed 2, one on the front and one on the back. Both of them are attached to Metal Gear high torque servo motors, as you can see, and we have custom waterproof all 3 of them. The method used is to open up the servo and fill up the circuitry with epoxy and to epoxy the outside. With this custom waterproofing method, each servo can withstand 750 millimeters of mercury or 9 meters of pool depth for 3 hours.
For this year's task, our robot utilizes 2 of our custom tools. You can see here a grout transporter, which fits easily into our front clamp and is opens like this above the cup to deposit the grout. It also includes buoyancy cone to help for any weight imbalances due to the grout when piloting. We also have our truck transporter, which can fit up to 8 truck frac and is turned to deposit into the area designated.
Our robot has 3 servo motors. Our first one is to open and close the front claw. Our first front claw design was about half as thick as the one you see here and did not feature a circular cutout in the middle. We added the cutout and increased the thickness so that way there are more points of contact when we grab objects, such as the trash screen in task 1 or the wire sample in task 2. Our second servo is to rotate the front claw. It uses rotation for the drop fry in task 2 or to grab various objects at different angles when necessary. Our third and final servo is to open and close the back claw. Our first back claw will look a little something like this, which is about half as long as the claw we have right now. We increase the thickness and the length in order to grab objects such as the tire more easily.
Can you turn it around so we can see the back claw while you talk about it?
Oh.
Thank you.
Yes. It's a change from this design to the one you see here is that the thickness goes all the way up to here because when we were testing this broke off. So that was an improvement we made.
Another use for our manipulators are the ability to measure historical artifacts like in task 3. For example, our front claw, when closed, is able to be inserted into the bore of the cannon. And so using these increments, we're able to determine the intent radius of the cannon. And we position ourselves angled, similar like this to the cannon, and we use the slants here to measure the outer radius of the front end. And using our back claw, we position ourselves with the back claw closed at the end cap of the cannon, and using the height, we're able to measure the radius.
In order to recover the can and lift back with use, we reused this lift back from last year in order to be cost efficient and also to help the environment. We did add some improvements though. We added this about $1 PVC piping in order to fit into the front claw, and we added this $2 PVC coupler which allows for water flow.
In order to detect metal and non-metal objects, we must acquire a metal detector. Originally, we planned on buying DIY kits and just soldering them together. However, after many trials, we figured out that they usually did not work to the range that we wanted to, or after a while, they became inconsistent and didn't work as well. So we decided to make our own board, this one, which is about twice as small as the ones we got, which we then fit into our custom holder onto the front claw. It uses pulse induction technology, which basically means it sends a pulse to the coil. It suddenly stops it, which sends a reflected pulse back into the chip. The duration of the reflected pulse is measured, and the duration can be changed by it being close to a metal object or not.
An accurate thermistor was added to the bottom claw for determining the temperature in the water sample for task number 2. For the cameras, we use 170 degrees wide angle backup cameras that we waterproof ourselves. For the front camera, we could see for the main localization of the ROV when piloting, but you can also see the front claw easily. In addition to that, we also have a secondary view of the claw pointed towards the upside, so that way that when we're grabbing large objects such as the trash, such as the screen for the trash rack, then you'll be able to see the bottom side. And then for the final camera, we have a back camera pointed towards the bottom claw to not only be able to see the back of the ROV, but also be able to see the bottom claw when grabbing tires.
The micro ROV body was made out of ABS rather than PLA because ABS is much more durable and is able to withstand potential impacts that could be faced inside of the piping. We use DST-700 motors for the micro ROV because they provide decent power to thrust ratio and they are also cost efficient. In order to waterproof these, we use silicone greasing on the bearings and epoxy on the motor core.
Our micro RV has a 2-motor configuration for forward, backwards, and left right movement. Our micro is designed to go up and down because within the 6-inch diameter tubing, it only goes forwards, backwards, left, and right. The micro has a slot in the middle where we can fit most of our electronics, which we then coat with epoxy. Our micro is connected to the main auto using 2 IP69K connectors.
Another key aspect is tether managing. The tether manager has a task of providing enough tether so the robot has a full range of motion without tangling it into the tether.
A major issue that we encountered a major lesson learned that for troubleshooting is when we were running our motors dry run. The motors produce back EMF, which we took that into consideration when designing the onboard housing. However, we didn't think that the actual EMF would go back through the tether and actually go through the control box. One day when we did our dry run testing, the EMF was so high that it fried one of the monitor controller boards. So we had to end up replacing that board, and then we used an oscilloscope to measure the voltage spike, which turned out to be less than 25 volts, enough to destroy the monitor, but easily avoidable with the same power supply that we use in the housing.
So this year we started off with a budget of $1,000, but thanks to the generosity of our sponsors, we only used $800 of the $1,000 budget, and we created an ROV that was worth much more than the $1,000 budget. In order to get sponsors, we email companies directly and ask if they want to become our sponsors. In addition to that, we created different levels of sponsorships, which included adding their logo onto our website and giving them publicity. In addition to that, we made most of our parts rather than just buying pre-made.
So by building most of our parts rather than buying pre-made, not only were we able to go through the design process and have a lot of trial and error throughout the way to change the designs, such as the claw, but we're able to learn a lot more, and we feel more proud, when we present a robot that is fully built by a company. So this is the accumulation of 3 years worth of hard work. We went from building PVC robots with Biotron motors to the advanced vehicle that you're seeing in front of you now. So now we would like to invite you to come closer, look at the robot, and ask any questions if you have any. All right, thank you.
All right, well,
Good job.